DNS, which local resolver the user is using. And the way you do that is with DNS Rum. So DNS Rum is a one-time use domain. It's usually, sometimes a wildcard domain. It's long, ephemeral, usually a short TTL. Looks like that, really long gobbledygook. It could be a dual stack record, a v6 record, a v4 record. Whatever it is it busts through the cache. And by doing that, you know exactly what resolver that user is using at that point in time. You then gather telemetry from that user about, say, your CDNs. And that's the measurement phase. And so the browser, the client will go and measure out various CDNs to figure out which one is closest, which one is most available, which one is the best throughput. And then on some implementations, all that done is done on the server side. You look at TCP handshake timers or TCP timers. We'll go, with this explanation, we'll use the server side version. And so that is then reported back to Rum DNS. Rum DNS churns it in real time and then uses it for actual decisions. So queries will go to the DNS platform and the answer will be based on that data. So for the rest of the talk, when I talk about Rum DNS, I'm actually referring to a product called Sedexis at LinkedIn. Nonetheless, the points I make are applicable to all types of Rum DNS steering. Virtually every single DNS platform out there, the public ones, have a Rum option, and they keep getting better all the time. And so just keep that in mind. These principles apply to virtually all implementations. So I want to use a fictional example of how you can do this. So we'll go with Comcast in California. Again, this is all fictional. So for Comcast in California, there are two CDNs, the blue CDN and the orange CDN. And in the first half of the day, the blue CDN is really fast. But then the second half of the day, the blue CDN gets kind of slow. And the orange CDN has the exact opposite behavior. If you have only one CDN, the orange CDN or the blue CDN, you'll have on average about the same performance at the end of the day. But if you pick the winning CDN at the first half of the day and then the winning CDN at the second half of the day, you end up with more wins. Now imagine you're not just doing this for Comcast in California, but you're doing this for Comcast in every state. And you're steering every state differently based off data. And then you're not just doing it for Comcast, you're doing it for all ASs. You end up with actually a lot of wins. And so this is one of my favorite graphs in the whole presentation. So in this particular graph, this is outside of China, this is globally. We use 3 CDNs, Edgecast/Verizon, Akamai, and LinkedIn CDN. And they're all in blue. I won't tell you which is which. However, what our members actually experience is the line in green. If you intelligently pick a CDN for that network, you can have a better performance than if you have one CDN. And the analogy is a bunch of horse races, right? Imagine every ASN segment or network segment is a horse race. You can pick the Akamai horse and you'll get a lot of wins. You also will get some losses and they kind of cancel each other out. You can pick the Edgecast horse. You can win some races and lose some races, or you can just pick the winning horse for each race and you end up with a lot of wins. So far I've been talking about latency, but there's also availability steering. So here's another graph. So at LinkedIn, we use a lot of third-party services and we qualify them. We're very careful about who we pick, and so they have to go through some sort of bake-off. And in this particular case, we were trialing a bunch of new CDNs, and we just put them in production, send real users to the CDNs. And one day in the middle of the night, one of them had an outage. It's a rolling outage in different pockets of the world. And unfortunately, our monitoring was set up to SMS the on-call instead of call the on-call. And so our on-call slept through that. They got up in the morning and noticed that there had been some sort of an outage, but no user impact. And so we looked at the data and we realized that Rum DNS had detected the flurry of 500s. And so in this graph, you actually see the particular CDN that had an issue. And when it started spewing 500s, the Rum DNS platform was able to detect that and remediate it all in real time. So we've been using Rum DNS since 2014. Other companies have been using it since 2007. It worked so well for LinkedIn, we're like, all right, let's not just use it for CDNs, but let's use it for POPs. And so what we started to do is to measure the latency from our users to their POPs. And so exact same thing as before, except now we're talking about POPs. So now, I think I double-clicked. I'm going to have to, okay, there we go. So this is, again, one of my favorite slides. These are the DNS responses for a DNS recursive resolver here in the US. This belongs to a really large computer chip manufacturing company. It's a global company, lots of employees, yet they take all their DNS requests around the world and send them to a set of resolvers here in the US. And these are the answers for this US resolver. The resolver is here in the US, it's physically in the US, it's network-wise in the US, it's geo-IP-wise in the US. And with geo-IP, all you can ever do is hand out North America Anycast, because that's what you get. The resolver sends you a query, you go, okay, it's in the US, I'm gonna hand out North America Anycast. But it turns out that this company has a lot of employees in India. In fact, they have 7,000 employees in India, according to LinkedIn. And so this is what the queries actually look like, the answers look like with Rum DNS. During the US day, North American users are the majority users, and so they're voting for North America responses. But during the India day, when India members come online, they become the majority operator or user of the DNS resolver, and they're voting for the Mumbai POP. And so rather than handing out North America Anycast, we just hand out North America. And this transition between North America and Mumbai happens automatically. There's no user intervention. It's really the members and the users telling us what's best for them. So we ramped in May. If you go to www.linkedin.com, it'll be a CNAME to the Rum DNS platform. We ramped in May. Anytime we make DNS changes, we are so scared of those because a lot of stuff happens during DNS changes. So we ramped for a week. What you're seeing are the last 5 days of the ramp. And in red is it's an A/B test, right? So users are grabbing an object from GeoDNS, and when they grab that object from GeoDNS, they have the line in red. When they're steered with, and these are Indian members, by the way, when they're steered with Rum DNS, they actually get better performance because they're steered correctly to the correct POP. And what's interesting is that when we ramped India to Rum DNS, there was no performance improvement. We actually knew that would happen because of all the testing we did, and the reason is because of flaws in GeoDNS. We actually had to ramp the entire world onto Rum DNS, and that's that ramp over there, a North American ramp. We ramped North America last. We ramped the entire internet space onto Rum DNS. It was able to pick out exactly which subnets and which network segments should go where, and that's why the improvement in India only happens when we ramp the entire internet space. So this is actual LinkedIn data from the LinkedIn feed. So as you guys navigate on the LinkedIn feed, we collect telemetry. And this is the 50th connect time for Tata in India. And we see that when we ramped, not India, but North America, so basically the last ramp of Rum DNS, we saw the lowest connect times in our system. Same thing with Korea. When we ramped Korea to Rum DNS, lowest connect times. And not just, by the way, we saw improvements across the board in many countries, especially in Asia. So Korea was very interesting because this is a distribution of POPs that we were sending users to. We were sending users to Singapore, Hong Kong, but also North America. Interestingly, there were a lot of ASs during the ramp that preferred North America. Not shown here is on June 16th, there was actually some sort of change on the internet where suddenly Singapore and Hong Kong then became the dominant answer that we handed out. And I love seeing these changes because it just goes to show that the internet is a living and breathing organism. Same thing with the UAE. UAE had the lowest connect times when they ramped to Rum DNS. The interesting thing with the UAE is that virtually all traffic comes from 2 ASs. Most countries have a dozen or hundreds or sometimes thousands of ASs that traffic comes in from. But the UAE only has 2, so it makes testing very, very good. It's a great case study country. So there's 2 ASs in the UAE. There's Etisalat, which is the really large one, and Du, which is the smaller one. And with GeoIP, we could only target by country, by country block. And so we would actually send the whole country of the UAE to India because Etisalat had underwater cables. And so that's with GeoIP. You can only target by the country. And so unfortunately, users on Du were being routed incorrectly to Mumbai. It was a worse experience for them. But with Rum DNS, we actually see the ability to cherry pick users on a particular AS and send them to the right location. So you can see Etisalat going to Mumbai and Do going to Singapore, all automatically. We actually failed out of Mumbai a few times for less than a day, and then once larger than a day. And what you see is that when we failed out, Do keeps going to Singapore, but Etisalat just goes over to London. So we talked about latency steering now. We're now looking at availability steering. So we have a POP in Sydney, and we have a lot of monitoring on that POP. And monitoring in that POP and on that POP, but we don't look at the last mile or the middle mile. And so what we have here are users on Vodafone and Telstra telling us that our Sydney POP are fine. All our monitoring shows that Sydney POP is fine. But AAPT, the third largest ISP, a LAN ISP in Australia, detected some sort of availability issue. We're not sure what that was. It might have been a middle mile or last mile issue, but only users on AAPT detected that. And so what we end up doing is the Rum steering platform looks at what other POPs are available in the area, and Singapore and Hong Kong are available. Because Sydney is less available than Singapore or Hong Kong, only users on AAPT get routed via DNS to Sydney very quickly. And so here's that outage, and then here are the Rum decisions. You can see AAPT switching over from Sydney and then to Singapore. So we've had a few versions of Rum DNS. This is version 2. Version 1 is very simple. It was done in the summer of 2016, and it just did the fastest thing. We love GeoDNS, though, because you can have a lot of programmability, a lot of health checking, a lot of logic. And so we put a lot of that logic that LinkedIn needed into version 2. And one of the things we accounted for was Africa. Africa doesn't generate a lot of measurements, so we put these overrides, thinking we knew what we were doing. We said Africa should only go to Europe or North America. It turns out that we log all our queries, and so if you do a dig, we'll have a log of it, and we can actually see where we routed people. But the platform always knows the right answer, and so it turns out that we put in an incorrect override. For Kenya, the right answer was not to go to Europe or North America. And so when we put all this data into ELK, we can actually see 3 large ASs in Kenya complaining every time they get misrouted. And so we looked at that, we said, okay, our overrides are incorrect. And so what we did is just for Kenya, we allowed them to go to Mumbai. And the reason they can go to Mumbai is because they have submarine cables going to CCOM directly. And so if you do any Looking Glass or Hurricane Electric, the BGP match, you can actually see them connected to India. And so this is the largest, one of the large ASs in Kenya called Jami. And when we ramped them to Rum DNS, again, the lowest connect times in the system. So a lot of this talk has been about redundancy. The earlier talk today was about redundancy, and we really care about redundancy. And one thing that we have at LinkedIn is something called Nurse. And Nurse is an auto remediation platform that looks at all our metrics coming in. And if for whatever reason the Rum DNS platform is being DDoSed or is unavailable, we're able to un-CNAME it within moments, and we fall back to GIP steering. The last thing I want to say about this is that DNS GSLB is evolving, and as software-defined networks continue to mature, I expect data-driven steering to continue to proliferate across DNS platforms. Thank you very much.
Thank you. Any questions? Going. Okay, thank you very much.
All right, thank you.
Thank you. Peter? Peter? Right. Peter Spacek. My Czech is horrible.
Spacek, if you want.
Spacek.
Sounds more universal.
Sounds more universal. Running DNS route on local host and its implications.
Oh, okay. Go on.
And you're good for time.
Well, I will wait for slides, maybe. Anyway, this talk is going to be about a route on the loopback, which was for a while considered a good idea. And we will look into some experimental data which shows that it might not be that good idea. So first, the motivation is basically the problems mentioned in the RFC itself. After motivation, we will look how the root on loopback compares with the aggressive use of cache. And then we will look into some possible improvements for the aggressive caching, and then I have some news. Even the authors of the RFC 7706 say honestly that it's maybe not a good idea because 7706 must not be the default configuration. And that was a big motivation for us to look into alternatives for 7706. One of the alternatives we considered is the aggressive NSEC. To compare aggressive use of NSEC and root on loopback, we need to compare the goals. So goals of the root on loopback, according to RFC, is first, faster negative responses, mainly for the junk queries, and then preventing queries from being visible, which is, in my opinion, kind of questionable when you have query minimization, but whatever. One of the possible side effects of running own root on loopback is, in theory, higher resiliency, but it would require proper implementation, which is not really easy. Now we need to compare this to goals of the aggressive caching, right? You can see that the faster negative responses are in there, so that's fine. Aggressive caching could provide faster positive responses for wildcards, but that's not interesting for root, so it's not relevant. And one of the side effects of aggressive NSEC are also like hidden queries or hiding the queries. Again, take into account the query minimization. The main difference is that the aggressive use of cache very much depends on content of the cache and on the query pattern. So it's not one-to-one comparison, it's not apples and apples. So goals are shared between the two RFCs, so that's good. And my guess would be that the aggressive NSEC would work real well, but we need some data to support this. So we devised an experiment which is basically taking PCAPs with real traffic, replaying the traffic to the resolver, logging the cache accesses of that given resolver, and then analyzing the cache access patterns with the focus on the queries regarding the nodes which belong to the root zone, of course, because 7706 is just about the root zone. As I already mentioned, the aggressive use of cache very much depends on the queries you send to it and on state of the cache. So all the results depend on the data set you use, so please keep that in mind. For this experiment, we had two kinds of data sets. One was a PCAP from our public resolver, which is run by CZNIC, and that's modest resolver with steady flow of queries. And then we had small data sets from two households just to compare how it would work with a really small resolver. For this experiment, we needed kind of special tools. One of them was a resolver which is logging cache accesses, because that's not what you usually enable. And then we used Jerry's perfect tool to reply the PCAP to the resolver. Thank you, Jerry. And then to analyze the log with the cache accesses, we used custom Python script, which is simulating the normal cache and the aggressive cache. At this point, it's important to note that the simulator is using unlimited cache size, so it's kind of optimal behavior, so the best case. Now fast forward to the results. For the data set from households, it's basically nothing, it's just noise. The traffic from households towards the root servers is so small that there is basically nothing to analyze. Everything is covered in noise. So for households, we can say that 7706 or aggressive use of NSEC will not make any significant difference. That's it. In the rest of the talk, I will be focusing on the public resolver, which is a very different story. On the public resolver, the aggressive use of cache is like the absolutely perfect thing you can do. It's the showcase for the RFC. When we focus on the root data, the average cache miss ratio was 0.25%, which is perfect. It translates to approximately 3,300 cache misses per day, which is about 6,000 UDP packets between the root servers and the resolver a day. And you can look at this number from different perspectives. It practically means that the public resolver during the course of one day downloads about three-quarters of the root zone into its cache. So here are some hard data. On the horizontal axis, we have time. In time 0, the cache is empty and we just started the resolver. And then we have hours as they go. And on the vertical axis, we have a hit rate for the data which belong to the root zone. The black points on the graph are the standard cache, and the red points are the aggressive use of cache. You can see that the normal caching has average, or hit rate for the normal cache is varying during one day, somewhere between 79 and 94%, approximately. It very much depends on the data. And for the aggressive use of cache, you can clearly see that on average, the hit rate is way more than 99%, which looks perfect. We can see that there are sharp drops in the hit rate after 24 hours. We will look into that. And the weird period on the hit rate on the normal cache is for now unexplained. That needs more research, so I will skip that. So now we will focus on the aggressive use of cache. You can see the sharp drop after 24 hours. So there are some data points which are marked specially. And you can see that after 2 minutes from the start of the resolver, the average hit rate is about 85 or 85%. After 4 minutes, it goes up to 94%. So it's extremely sharp increase in the hit rate when we are focused on the root zone data. After a couple of minutes, it gets to 99% or more. And after 24 hours, it sharply drops again, and it starts climbing. And in a couple of minutes, it's back on 99%. So what's the explanation for this? If you look into the root zone content, you can see that the minimum TTL in the root zone is 1 day. And on the previous graph, you have seen that the hit rate is extremely sharply going up, which basically means that the public resolver will fill most of its cache during a couple of seconds or minutes, which means that all the records will expire after 24 hours again, and the expiration will happen in a couple of minutes. So it leads to the sharp decrease and then sharp increase, of course. And on the graph, you can see that the decrease is kind of getting smaller and smaller, and the hit rate is getting smoother and smoother. So after 4 days, hit rate doesn't go below 98% on average. So it seems that we have explanation. Data are consistent. What we see is consistent with what we would expect. That's a good sign that the experiment kind of works. And when we are looking into the root zone, you can see how the root zone is big, and that zone transfer requires less than 400 packets. So if we return back to the goals of the RFC 7706 and the aggressive NSEC, the aggressive NSEC can certainly provide fast and negative responses. We have seen that on the graph, and is definitely preventing queries from being visible. The caveat is that it's not these like improvements are not available for all the queries, but there is 0.25% of queries which don't get this benefit because we have empty cache or the cache expires. So let's see if we can do something about that. Empty cache is a problem, right? We can do the zone transfer, which is required for 7706 anyway. So if we had a mechanism which would pre-fill the cache from the zone transfer, we could get the hit rate to 100%. So using some hack which downloads the root zone and fills the cache before, we have 0 miss rate. And if we repeat this cache filling every 24 hours or right before the cache expires, we can get 0 miss rate. Right now, it's important to realize that we are talking about the resolver, not about the authoritative server. And the resolver is concerned with TTL. So because the minimum TTL is 1 day in the root zone, we could theoretically do the cache filling once a day and repeat that right before the 1-day TTL expires. And in practice, it would mean that the recursive resolver would require only 6% of the communication with those root servers when we compare the cache pre-filling by zone transfer with the aggressive use of NSEC, which does the normal queries whenever there is a cache miss. So pre-filling looks like a good idea, more or less. And then the last thing, which is theoretically provided by 7706, but it's not provided by aggressive use of NSEC, is the theoretical possibility of high resiliency against the root zone or higher resiliency against problems with communication with the root zone. And when we have all the data in cache, it sounds kind of easy to implement a variant of serve-stale draft and just serve the data from cache, because when we have everything, there is something we are missing, right? To conclude, it seems that 7706 is not really a good idea, at least to me. So for a not resolver, we decided to replace 7706 with custom implementation, which includes aggressive use of NSEC, some cache pre-filling mechanism, and possibly a variant of serve-stale, but that's in future. In any case, look to the bright future. In 2018, we intend to deliver all this together in not resolver. And that's all for me, and I think that we have still some time for questions, right? Okay.
We certainly do.
Hi there, I'm Brian Summers from Open DNS. So, I don't know how to describe this. We had the same problem for a different reason with a different result. So we had a problem where people were looking up top-level domains of 000 to 500. So all the numbers in between that range. And they were looking them up very frequently. They looked very like IP numbers, but they went up to 500. And they were 4 octets, or 4 words, I guess. And the result of this was that they were hitting our DNS resolvers with all this traffic. We were hitting the root zone servers, and we were getting tar-pitted from the root servers because we were sending them so many queries that were all negative responses. So we had to figure out what to do about this and kind of visited the same RFCs. But what we ended up doing was doing the pre-fill option. And so I forget where the resource was, but there's a way of downloading the root zone file, which we download every hour and reload into all of our resolvers so that we have this pre-fill. And it, as you suspect, results in 100% hit rate. And in fact, we turn off the ability to query the root servers. So we don't query the root servers at all, but there was a lesson to be learned in that things can go wrong. So if you can't parse the root zone file for any reason, or if something else goes wrong, you want to be able to flip a switch to go back to the normal behavior, which is what we did as well. But yeah, I fully support the pre-fill case.
Okay, thanks for sharing.
Paul Hoffman, ICANN. So I propose that your solution is simply turning 7706 into 8198. That is, that you're saying, pull down, do what you were doing in 7706, but don't, since you're doing AXFR, you're not necessarily going to get the DNSSEC protection. And it's really likely if you're doing AXFR, then you're going to be really reliant on the root zone that you're talking to want to always do AXFR with you and such. We, Warren and I, plus the working group behind us, really talked a lot about the fragility in 7706. I think that your fragility list will look a lot like ours and be slightly longer, which is not to say it's any worse, because our list is really long as it is. Andrew, sitting in the back, was beating us up mercilessly on everything that we were sort of short-circuiting there. But I would propose that you actually abandon AXFR. It is, I mean, of the many things in the DNS protocol that people here laugh about and how it's done, and oh, but then if it's this many records long, you have to look at this and such like that. We do have things like, HTTP and such like that, which is, and you'll notice in 7706, we were saying to people, get this over a reliable transport. It's the new internet, we know how to get that. And at that point, I think really you will see that the two are quite similar. And I think that that's just great.
Yeah, my reply to that is that we are talking about cache preflink. I'm not saying that it will be zone transfer, right? I'm intentionally
like
using cache preflink mechanism.
Right, and again, I think you will see that you are becoming the moral equivalent of 7706, which is just fine, except for your no there. So,
yeah, the thing is that when you approach the problem as cache preflink, whenever it fails, it's just cache, right? So you have cache full of expired records and you just do the normal recursion,
right,
or whatever you would without the cache preflink.
Yep.
But thank you for the comment.
Hi, Daniel Kahnberg, RIPE NCC. Let me do some heresy here. I'm an old-style engineer, and I go for usually the simplest solution to anything. And all the 7706 and 8198 seem overly complicated to me. We're talking about the root zone. The root zone has typical TTL of 6 days. Yeah, you have minimum TTL of 1 day. I'd like to see which records these are. But what I do at my home, and of course, yeah, it's not a big, I download the damn thing. I think I do use AXFR every couple of months or so. My users haven't complained yet. Because you have to really, and maybe I'm facetious a little, but even if you run a bigger resolver, the rate of change in the root zone is really, really low. So what you could do is, like the first speaker said, download it. Download it not even once every hour, but once every day is fine. And I don't think you will have any problems. Serve it authoritatively and be done with it. And don't do any of this, studies in the 0.25% and whatsoever. It's a solution that would work. Just to be totally facetious, different. Choose the simple solution. And you can AXFR it, you can HTTPS it, you can, it's not hard to come by, the root zone. And if there's more demand for downloading the whole zone, I'm quite sure ICANN and others will stand up the right resources to actually get it reliably.
Thank you for your comment.
Ola Gomson, Cloudflare. Yeah, this is very good, very nice. You proved that we were wrong about doing 7706. beauty of negative NSEC processing is that you get all the data, and you have one app out on the net that makes sure you have all the root zone in cache, all the NSEC records in cache almost instantly. But how much worse will this be if Google Chrome changes its behavior with detecting if their network is lying to it or not for NX domain?
We'll see.
How much of the traffic was just single label into the root zone?
Well, the thing is that on the public resolver, we see a whole lot of crap, not only from Google Chrome, but all over the place, including queries for the binary something you can't even see that in command line and so on. So it's like not just Google Chrome out there. We had a LG washing machine sending weird queries in pcaps and so on. So
okay. Okay. So yeah.
Yeah. Thank you for comment.
I disagree with Daniel here that I think AXFR to the resolver is obsolete if you do aggressive NSEC.
Thanks.
Brian Dixon. I'm wondering whether, for the cache expiry, whether Hammer, if you're familiar with Warren. Yeah. Yes. But the other thing that just occurred to me when I was standing in line was identifying what changes or what has been added to the root zone could be identified using just walking the NSEC records. Since you probably want to be doing refresh on those anyway, you would identify when new things have been inserted in the sequence, and that probably be as good as anything, and then you just simply query for all the record types for each of the things that you discover, and then refresh.
Yeah, we plan to consider that, but up to now it seems that it's just more complex for little benefit.
So, Warren Kumari, I suspect all of this is my fault. 7706 and 8198 and Hammer, so oh dear. So, the motivations which are listed in 7706 for why you should do this are not the full set of actual motivations. Yep. Well, actually, when we had this discussion, one of the motivations was there were a number of people who said that they were in environments where they could not get access to a root server at sufficient speed or at sufficient reliability. And this was not really a technical argument, and this is not really a technical solution. It was a...
Sure.
Yeah. Okay, cool.
Yeah, there is no technical answer to political problems, okay. Right? Okay, thank you for your questions, and I will use last 2 minutes to thank Ondřej Suri, who started the project. As you may already know, Ondřej Suri decided to change from CZNIC to ISE. Apparently, after 11 years and 11 months with CZNIC, it was enough. So thank you, Ondřej, for starting both projects and pushing them forward. And for all of you who fancy not projects, I would like to say that the projects are going on even without Ondřej, with new leaders. Not DNS, the authoritative one, is led by Daniel Salzman, and the not resolver is led by me. And now we have to prove that we can do something without Ondřej, right? So. Not DNS 2.6 was released today. It has some nice features, including automatic DNSSEC algorithm rollover, and the not resolver 2.0 will be released next week with the aggressive use of validated cache. So look forward to that, and thank you for your attention.
Thank you. Do we have Diana? We have a change. Somebody. Same talk, different presenter, DNS service monitoring at Salesforce.
Okay, thank you. I'm Han Jung from Salesforce, and today I'm going to talk about DNS service monitoring at Salesforce. And this is the work we did with our intern Diana this summer. She studies at UC Berkeley, and she's currently working on her midterm exams. So she's not coming today. I'm going to talk. So today's talk will cover why do we want to monitor our DNS service and what we monitor, how we monitor it, and we will also share some interesting and surprising results. So Salesforce is a software as service company, and we have been used managed DNS service for a long time, associating with our data centers. Because we are a cloud company, DNS plays a very important role. It has to be highly available. However, in the past several years, there were lots of DDoS attacks happening, and that made us to make the decision to use multi-DNS vendors. And because of our choice, we were not affected by the last year DDoS attack. At Salesforce, we applied two types of multi-DNS vendor configs. The first one is primary, secondary. And the second one is active-active or primary-primary. So that means we use both of the two DNS vendors as primary. And when we need to make some changes to our zones, we update the zones to both of these vendors. And CNAMEs plays a very important role at Salesforce because it redirects our customers to the specific data centers where have their data on it. And also, CNAMEs is also used by set switching and migration. So now I'm going to talk about why do we want to monitor our DNS service. The first reason is we want to monitor our service status and performance. We want to make sure our name servers, DNS services is always available. And because we have multiple DNS vendors, we can benchmark them and compare their performance. And then we can share our results and reports with them. And they can help improve the DNS services for us. Monitoring DNS services also helps find some hidden problems. For example, some undocumented REST API behaviors. So I will use some interesting and surprising results to show examples for all of this in the later slides. We monitor our DNS services from three perspectives. The first one is availability. We want to make sure our name servers are always available and respond to DNS requests. We also want to make sure the REST API of our vendors is always available. For consistency, we monitor whether the name servers from a single vendor are inconsistency. And when we apply primary and secondary, we want to make sure all the name servers from both our primary and secondary are inconsistency. The last one we monitor is update propagation delay. So that means when we update our zones, how long it takes before we can see the changes, the updates on the name servers. So first, I will talk about the monitoring of availability and consistency. For availability, we periodically send DNS queries to all the name servers using UDP and TCP to see whether they respond to our DNS requests. Similarly, we also periodically send log in to DNS vendors using the REST API to make sure it is available. For consistency, we periodically send SOA records to all of the name servers and compare the serial number to see whether there are inconsistency. So now we know what we want to monitor and how we want to monitor them. The next question is how we can show our results, how we can monitor them. We use two tools to show our monitoring results. The first one we use is Refocus, developed by Site Reliability team at Salesforce. It's open source tool, and it has been used by many companies. So it shows the real-time status and performance of our monitoring in different colors standing for different status. And the good thing of Refocus is once some status changes, for example, a name server is down, the color here will change and blink, attracting more attention there. I do want to share some results. We started our monitoring since November last year, and currently we have about 6 months of data set. we have lots of results we can share, but I really want to focus on the results for the legacy name server only. So legacy name server means the name servers that do not have the latest SOA records. So in this specific scenario, we monitor the primary secondary config, and I'm not going to tell which ones vendors we are monitoring. So we use vendor A, B, and C to stand for them. And in figure, we compare the number of occurrences by two vendors. The green one is the primary, and the blue one is the secondary. So from the figure, we can see the primary has less occurrences. We also found that when there was legacy name servers, the average lag time for the primary was about 3 minutes, but it was about 17 minutes for the secondary. And we also have some interesting findings. The first one is some primary vendor servers also lagged. And sometimes only the name servers from the secondary vendors have the latest serial number. So this is the reality of applying multiple DNS vendors. And there are some trade-offs for our DNS vendors, and we understood that. And we also share our results and reports to them, and help us a lot to improve the performance. So this one shows some diurnal patterns for the consistency. So one unexpected thing here is we saw more name servers during the nighttime compared to the daytime. So one possible explanation is we may do more maintenance, or our DNS vendors do more maintenance during the nighttime. For monitoring of the update propagation delay, we periodically create CNAME on 3 DNS vendors using the REST API. And then we query the CNAMEs immediately after we created the CNAME, 3 seconds and every 10 seconds until 4 times. To see how long it takes, we can see this created CNAME on the name servers. To show the monitoring results here, we use a different tool, Argus, which is also developed by Salesforce. And this one shows the real-time status performance and the results. Also, it shows the historical information, so we can see the trend here. So this figure shows the update delay for 3 vendors we have. So from this figure, we can see vendor A has higher update propagation delay. So that's why we want to focus on the vendor A. So vendor A provides us with 6 name servers, and all of them have high propagation delay, especially for name servers 3 and 4. They always have the same delays. And there are some periodic fluctuations for these 2 name servers. And we talked to this vendor, and they helped me a lot to improve the performance. I will show how they help us in the later slides. So I've compared the average update delay here. So for when we consider 30 seconds as a reasonable delay. And for vendor A, about 15% of the delay is less than 30 seconds, and for vendor B and C, more than 99% of the delay is less than 30 seconds. We also saw some diurnal behavior here, which means vendor A has higher delays during the daytime. So now I'm going to show how our vendors help us to improve the performance greatly. So we shared our results and the report to vendor A, saying these 2 name servers have higher update delay, and they responded to us very quickly, help us to improve their update delay significantly. We can clearly see the reduce of the update delay from this figure. Monitoring DNS services also helps find some hidden problems. So currently, we use vendor B as our secondary DNS vendor, and we are considering to use it as the primary. So we are curious how the performance will look like. But we found that sometimes the CNAMEs could not be created. So we talked to this vendor, and now they are working on it to help us to solve this problem. And all of our DNS vendors responded to us very quickly and helping us. So we do we do learn some lessons from applying multiple DNS vendors. A very important one is all these vendors have different behaviors, but all of them are really helping us to improve our services. So I want to say thank you to all of them. And so we monitoring DNS services also helps to improve the performance and find some hidden problems, as I showed in the previous slides. We do have some future work to do. We want to do more monitoring, for example, for IXFR, AXFR, and the DNSSEC. And currently, our monitoring system is deployed in single vantage point. We plan to deploy the system at multiple vantage points around the world. And we will continue working with all these DNS vendors to improve the performance. And thanks.
Thank you. We have a few minutes for questions, if there are any questions on that. Evidently not. Thank you very much.
Okay, thank you.
And finally in this session, Casey, run, a study of DNS rate limiting deployment from Casey Decchio.
What's that? Okay. All right, we got them up there. Great. Good afternoon, everyone. Casey DCO from Brigham Young University. Today I'm going to talk a little bit about DNS rate limiting and some experimentation we have done to see how it has been deployed. So I'm going to start out today just with a little bit of review of the attack model and some of those solutions that have been proposed. Then we'll go right into response rate limiting and talk about some of the measurement techniques that we've used, and then finally show some of our results that we've seen. We consider this somewhat preliminary in that we're still investigating some of what we're seeing, but we wanted to show it here at OARC to not only show what we're seeing as we're learning about it, but also get some feedback. And if you have any ideas as to what might be causing some things, that would be interesting. So just to review our attack model here, our typical DNS reflection amplification based DDoS attack involves a number of attackers or compromised machines, or bots, however you might like to call them, that are sending spoofed queries with the address, the source address of another being the target, towards different DNS servers, which are the reflectors. And these reflectors in turn return the responses then to the victim, who becomes overwhelmed with all these unsolicited responses. Okay, and of course you multiply this by many, many attackers and many, many reflectors, and the victim becomes overwhelmed fairly quickly because of lack of resources to deal with them. That is, in summary, our DDoS attack using reflection. Now, there are several perspectives that we consider when we start looking at solutions to prevent or mitigate reflection-based DDoS attacks. The first is the victim perspective, and you note there's a very short list on this. There are probably some other things, but ideally you're looking at either redirecting your traffic somewhere else, or otherwise increasing your resources, and it becomes cost prohibitive to do this. And many of you out there have been on the front lines and actually doing this and know much more about it than I do. But from a victim, you are very, very limited in terms of what you can do. But there are other perspectives that we consider. Many of us are familiar with BCP 38, which is the idea that you stop these right at their source. And when I say these, I'm talking about the spoofed DNS requests that are leaving the network. If you actually inspect the source address as they're leaving and note that it's coming from someplace other than the source from which they're being sent, you can actually drop them right there. And we will continue beating this drum of BCP 38, and yet it does not have the deployment that we would like it to have. But this is the perspective. First, we talked about the perspective of the victim who's receiving it, which has very little it can do. There's actually very much you can do at the source side, but unfortunately there's not the same incentive to do it because it's benefiting everyone else, not those that are actually deploying it, and namely the networks on which the attackers live, these compromised hosts. Finally, we consider those in the middle, the reflectors. Okay, and when we talk about DNS response rate limiting, now I speak sometimes about rate limiting as response rate limiting, and then sometimes I speak about it more generically as rate limiting, because as you'll see in the results, there are actually many different configurations that we have seen as we've investigated this. But in the typical model that we've often heard about, responses are limited at the reflector here, or the DNS server, the potential reflector, I should say, based on a certain threshold when you see a frequency of incoming DNS requests of a common domain name, and we're talking query name, query type, and source IP. Okay, and the responses that are then returned to the requester or the victim in the case of a reflection attack can be small because they are truncated. And this allows the clients to still have a reasonable chance without overwhelming them with, if they still want to get legitimate requests to the server, they can still have a reasonable chance of being responded to because of these occasional requests that are being sent back. So that's the idea behind response rate limiting, kind of in a nutshell. But the point of my talk is not to go over that in much detail, but show kind of what we've actually seen in the wild in terms of behaviors. So in terms of what we have done in our experimentation here is we wanted to, and actually let me just pause for just a second. There actually has been some previous work here, and so we're not the first ones to have done this, but we have gone in some depth that maybe others have not. So maybe looking at, others have maybe looked at thresholds, and I'm sorry I don't have them up here on the slide, but we've tried to go in and actually look at additional configuration components of these deployments of response rate limiting. Okay, so what we did was we actually looked at, we had the root zone, the top level domains. At the time there were about 1,300 or so when delegations within the root zone, and we looked at those. And then we took zones associated with a website analysis place called StatVu, and extracted about 900,000 of those. And then taking the authoritative servers for each of these zones that we extracted, we came up with about 3.8 million zone server pairs. So we looked at, for each authoritative server that we found, we queried it once for each zone for which it was authoritative. Okay, and we looked at both IPv4 and IPv6, and we'll show you what some of those results look like. Now, one question that we might ask is why is this interesting or important? There are two main points that I bring up as to why we might be looking at this, and one of them is because these are among the efforts, just similar to how others are looking at BCP 38 deployment and how well that is going, namely the spoofer project. We feel this is important to kind of quantify our efforts as to how we're doing to combat some of these abuses of the DNS and other protocols out on the internet, and how we're doing, and hopefully to help motivate others and see if we have critical mass in doing this, and also maybe to look at how effective we're being. Also, one of the more interesting aspects of this, when I go back to perspective, we have the victims who were kind of on the far right side that are really feeling the pain of this and yet don't have a whole lot. And then you have on the far left side, which I showed earlier, the attackers networks, which are not feeling much, but yet could have the most impact. And somewhere in the middle is this group, the reflectors, or the potential reflectors. So what this represents when we're looking at this is someone that maybe isn't on the feeling the most pain, but they are feeling some of the pain. So looking at this represents, in some cases, some of the more altruistic efforts to help, because it's not directly benefiting the reflectors per se. Some of you may disagree with me, and that's okay. But in general, it gives us a sense of who's deploying things for the good of the community and not just for their own benefit. And so I think that's actually important for future efforts that may come out in combating abuse. Okay, So moving on here, looking at the methodology, as you suspect, or might suspect here, where the way we did this was actually for each of these servers and domains for which it was authoritative, we sent a burst of queries in parallel to it. Okay. Now we wanted to minimize impact. We didn't want this to look like an attack or look too anomalous, and so we just did it once. One burst of 500 queries within a single second. Now we realize there are some shortcomings with that because it's not prolonged. You're not going to see thresholds that go beyond that or other patterns that go beyond 1 second, but our intent was to minimize impact and hopefully not even raise any eyebrows. We did raise a few, by the way, but we didn't seem to really cause any problems. Most people saw our work and said, oh, when I explained it to them, they said, okay, carry on. Okay, so we sent 500 queries within 1 second. We were actually using queries of type A, because we didn't want to, I mean, typically you would see these reflection queries with the type any because of the size of the response, but again, we were trying to look at behaviors and didn't want to annoy anybody too much, or even DDoS ourselves for that matter. So, and we didn't use EDNS for the same reason, although we would suspect that A queries typically wouldn't, or the responses for A queries typically wouldn't exceed the 512 limit for queries without EDNS. We didn't want to take any chances and at least show people our efforts to try and minimize any impact, negative impact here. We also, in the case where a given server was authoritative for multiple DNS zones, we actually spaced it out so they wouldn't be done concurrently, both so it didn't throw off our experiment, also so it didn't look like we were doing much more than we were, and so we tried to minimize that impact. And then also in terms of transparency, we set up a reverse DNS from the IP addresses we were sending to be somewhat clear. We called them internetmeasurement.cs.byu.edu, so that hopefully you know, they would get an idea that we were trying to run some experimentation. We actually set up some websites with additional information, including how to opt out of our experiment. For the few that contacted us, no one opted out, so we just continued there. Okay, so in terms of what we saw once we did this, so we had a few methods for getting the threshold, at the point at which the servers we were querying stopped responding, at least using complete responses. You can see a few common cases here by the little jumps in the graph. So this is a cumulative distribution here. But what we did with this first approach was to take basically the total number of responses, complete responses, and divide them by the total number of queries. So it's somewhat of a naive approach here, but what it does give us is a percentage of the queries during this time period that were responded to. Okay, and so what we came up with, what you see on the left here is for T, which is the threshold between 1 and 490. Now we left out, there was a large jump between 490 and 500, and we believe that was in part related to normal response loss, perhaps because of the load we were throwing at things over that small amount of time, but we didn't feel like, we felt like it was significant enough to leave off, and so we just discounted about 2% of that. And what we found, the remaining, is that about 18% of these zone server pairs were exhibiting some type of rate limiting behavior, and the median threshold was about 200 queries per second. Okay, and you can see a significant, you can see a few significant jumps, one around 50, one around 100, you can see kind of a tiny one around 200, and so forth. But kind of interesting in this whole graph is that you can see kind of this almost uniform distribution in between some of those jumps, which is quite interesting to me. So our second approach, rather than just looking at you know, the total number of complete responses divided by the total number of queries we made, we were concerned that at some point we might, you know, especially towards the end where maybe there was some packet loss along the way, that we might have some false positives in there. But additionally, we wanted to see if you had packet loss around the time that you had a given, or if you had some packet loss in general in what we were querying, then you might also mistake the actual threshold that was being configured with something else, and so you may not have as sharp jumps in your graph here to show us what were common thresholds. The results were actually a little bit surprising and not quite what we expected. But the methodology we used to do this was, we used kind of a sliding window algorithm where when we looked at the queries, we ordered the queries that we did, and then we selected a window size. In this case, in the example here, we're using a window size of 4, although what we actually used in our methodology was a window size of 8. But basically, we take this window of our example here, we'll use 4, okay? So we slid along, and until at the first point in our queries in which we had the number of responses that were either missing or were truncated were less than, greater than or equal to, excuse me, the number that were responded to, we considered that our threshold window. And then our threshold became kind of the midpoint in that window. So basically, because of the out-of-order responses and potential packet loss, we wanted to find kind of the point in time where things changed over several rather than just at one given point. And that was the idea behind this. Okay, so this is what it looked like, and when we used a window of 8, this is what the graph looked like. It looks quite a bit different. It's actually smoothed out, which is not quite what we expected. We were hoping it would be actually have some of these jumps a little bit more refined. And what you see here is kind of the symbolic representation of what we were doing with this. It was just to make it look a little bit more fancy for you guys, because we know you needed that in the afternoon. Okay, all right. So actually the results were similar in terms of the total number that we saw that were rate limiting. In the previous example where we were using this collective approach, it was about 18% that we saw exhibiting rate limiting behavior. Here was about 17%. The median changed quite a bit though when we used this different approach. And we found that it was much more aggressive. And when we say aggressive, meaning we're talking a lower threshold before the servers started rate limiting. And in this case, it was 75 queries per second rather than the 200 that we saw in the previous example with the different approach. So, and about 25% of those rate limiting have thresholds between below 6 queries per second. Okay, so, and about 80% are less than 250. Okay, so very interesting spike on the far left there with this, I don't know what the default configuration is these days, but it seemed like it was around 25 to 50 or something queries per second. But we saw quite a few with the 6 queries per second. Okay, when we look at this slip rate, now I have modified what might be known as the common definition of slip rate, or at least the way I've expressed it here. But I've defined a slip rate, at least for the purposes of this, as the percent of DNS responses returned by the authoritative servers after the threshold was reached. Now I know this is expressed different ways in different DNS server configurations, but go with me here on what we're presenting. You'll note that there aren't a lot of real big jumps here. You see kind of, a fairly large representation at the very beginning, close to a slip rate of 0, where things just stop responding altogether. Okay, and that's about a third, actually, which responded to 10% or fewer queries after the query load was reached. Okay, and I think in configurations that would be somewhere around a slip rate of 3 in bind, and I'm not sure what it's called in unbound. And then there were about 40% of zone server pairs that responded to more than half the queries. Okay, and actually in at least some configurations, half is about the highest that you get. So this kind of second half over here was curious to me. If you look on the right-hand side of the graph, just the fact that you have this fairly linear slope from about 0.5 to 1 shows me that there's actually about 25–30% or so that are uniformly distributed across this. And so many different configurations in terms of what people are using for their slip rate after the threshold has been reached, which actually surprised me. And this is the truncation rate. So this is the percentage of DNS responses truncated by the authoritative servers after the threshold has been reached. So for about 86% of these DNS servers and for the zones for which we were comparing, there was no truncation used. So, but this also includes those that weren't responding. Does this include those? I believe, no, this does not include those that were not responding. They actually stopped responding at all. Excuse me, they were responding but without truncation. Let's see, and about 8% of zone server pairs truncated at least 90% of their responses. So typically you'd see, or at least in some of the literature that's out there, you'd see responses, all the responses that returned were truncated, but we didn't see that here. We saw a little bit of diversity in what we were seeing, including those that weren't truncating at all, about 86% from this group. Now, this was interesting. So when we started looking at consistency across servers, so for a given DNS authoritative server that was authoritative for more than one DNS zone, we saw consistency in about 60% of IPv4 servers and about 45% of IPv6 servers. But then you see on the far right-hand side, you actually see an inconsistency that's somewhat drastic for about 5% of IPv4 servers and about 10% of IPv6 servers. That means in this many cases, you have a given DNS server that is doing extreme rate limiting, as in, between 1 to 6 queries per second, but not rate limit for one domain for which it's authoritative, but not rate limiting at all for another one. Now, I realize there are different DNS architectures and configurations out there, but we did find this a little bit odd that there was inconsistencies across a given server for the different domains for which it was authoritative. But almost more interesting is the fact that you, again, have this kind of almost uniform distribution in the linear slope that you see from the far left to the far right, which indicates that there's a lot of variance and lots of different configurations across this in terms of consistencies between the different domains that a given DNS server supplies and the way it responds to them in terms of rate limiting. What that means, we're not exactly sure, except that it's not a given server does, in some cases, in many cases, it does treat a different domain differently, different domains differently. Finally, looking at IPv4 and IPv6. Okay, so for every DNS server that we were looking at, taking the name and when it resolved to both an IPv4 and an IPv6 address, and it did rate limiting for at least one of those. Okay, so that's our data set that we're looking at. It does IPv4, it does IPv6, that's our criteria, and it rate limited for at least one. What we did was we took the difference in threshold and graphed it here. So the large line in the very middle of this graph, that shows about 80% for which a given server had the same rate limiting threshold for both its IPv4 address as well as its IPv6 address, which we would expect to see. Okay, that's good behavior. But on the other hand, we actually, in the lower left, where the slope goes down from the middle to the left, we have about 15% for which the IPv6 had lower thresholds than IPv4. And I believe that actually should be higher thresholds, meaning that the v4 was actually doing things much more aggressive than the IPv6. So that's a typo in my slide there. And what that can lead to, and it's maybe difficult to tell without going into this graph a little bit more, but as we continue to gain traction in IPv6 deployment, we are trying to be mindful that we're not forgetting some of the lessons and deploying equally some of the things that we've learned in IPv4, and that includes response rate limiting and other types of defenses against abusive behavior. And so that's what we were trying to see here. In fact, you can see even 2% of these, we have an extreme threshold difference in which the the IPv4 servers had a very, very aggressive approach to rate limiting, and the IPv6 servers were not rate limiting at all in this particular case. And so, and again, this is the same DNS name server, or at least the same name, resolving to a given IPv6 and a given IPv4 address. So that's what we're measuring here. Okay, so just to wrap up and summarize some of the preliminary results that we have found, we found that rate limiting is deployed by about 70% of the authoritative servers on a per DNS zone basis from the domains that we have looked at in our given set, and that included TLDs and some of these popular website domains. We find that thresholds are fairly evenly distributed, with about a quarter of them being below 6 queries per second. And we also found some behavioral inconsistencies for DNS servers that are authoritative for 2 or more zones, as well as DNS servers that have both IPv4 and IPv6 addresses. So that is my talk, and I am glad to take some questions.
Thanks, Casey. Questions?
Hi there, Brian Summers from OpenDNS. So I found this interesting, even though we're not the target of this talk. We do recursive DNS, so we see a lot of attacks, some of which are amplification attacks like this, but we also have to deal with rate limiting on the upstream. So I'd kind of make one comment about our rate limiting implementations. One of the things that we do is we have flat rate limits for initial queries per client, but if they sustain their attack or their query rate, we reduce that rate limit so that over time they'll get to a situation where they're sending us 1,000 queries per second and we're sending one of them through to the target. So this kind of makes our targets happy, and the guy who's sending the queries doesn't know, right?
Can I ask you a question about that? So are you suggesting that we simply wouldn't have seen any rate limiting perhaps, or at least very, very little rate limiting hitting your servers given the methodology that we're using here? Is that correct?
Unless you sustain the attack, you won't see the full effect of the rate limiting, yes. Okay. And in fact, our initial rate limits for A queries is 512.
512 is your? Per
second, yeah.
Okay, interesting.
And that will go down by 10%.
So we wouldn't have even hit that limit with what we were doing. We thought no one would do above 500. No, and that's perfectly fine. We're learning, which is, I'm glad we're getting some feedback here. Thank you.
So one of the other interesting things with V4 versus V6, when we try to remember the clients that are querying us, we store it all in a hash, and the hash sizes are determined by the IPs that we're actually putting into the hash. It's harder to store V6. We don't make a hash that's 4 times as big. So V6 has more of a likeliness to overflow and forget people that are querying it. So we do have a graph that tells us that we're overflowing a lot, so that if we kind of overflow excessively, we can change the hash sizes. But it's just something that might be affecting V4 versus V6 in terms of rate limiting.
Just to be clear, is that at the load balancer that you're talking about?
That's at the resolver, just remembering who's been querying us.
Okay, I gotcha.
There was something that I had to say about when we query upstreams.
Oh, sorry. You're thinking of, so the clients coming in and how many times they've requested. You're just saying it's extra straight for V6 because of the address space size.
Yes.
Okay, yeah.
Yeah. And then in terms of us querying upstreams and being rate limited, I mean, one of the things that we've had to implement is the ability to ask one of our other resolvers, can they query that server if we don't get a response from them, just in case we've been rate limited, but they haven't, sort of thing. So we have this kind of mesh where we query each other. I've lost my train of thought of what I was going to say about the upstream. But yeah, as you say, it's very hard to determine why why given authority is rate limiting you. That's it.
Hey, thank you very much.
Hey, I'm Matt Mahan at Amazon Web Services Route 53. First, just a clarifying question. Maybe I missed some context, or there's an ROC I haven't read, but what is the expectation, your expectation for the basis by which DNS servers rate limit on client information, name being queried, zone being queried?
Yeah, so that's a great question, and there really isn't one answer. I think in the DNS community in particular, we've heard a lot about response rate limiting, which typically looks at query name, query type, and IP, that 3-tuple. But in our research, we initially just did it. We really were doing it with the same name, the same type, and the same IP address. In part just to get kind of a starter feel for it. So we were somewhat naive and limited in our initial experimentation, but again, we're trying to tread with caution without causing negative impact with what we're doing, and so, you know, we don't want anyone here to like shut us down or blacklist us because of, you know, we're trying to do this for good and not for bad. So the short answer is, at least with this experimentation, we couldn't experiment beyond that, but there are several ways to do it, and you know, the pros and cons are probably outside the scope of this particular talk, but yeah.
And thanks, you answered my other questions too. Much appreciated.
Thank you.
Alex Dupuy from Google. Thanks so much for doing this. I'm looking forward to also trying to do this also against recursive servers. We will not blacklist you. We will probably even notice, but at any rate, or if we do, you'll be measuring it, so don't worry. I guess the question I have is, you know, there's a certain tension, I suppose, between the rate limiting that's implemented by authoritative, and one of the problems that we have is that when the authoritatives limit queries from us, that sometimes doesn't end well for anybody. If you have ideas about that, I mean, there are, you know, definitely some possibilities, DNS cookies, things like that, that could potentially be helpful. But some kind of signaling mechanism or back pressure or something like that as a way of indicating, yeah, you're asking too much. And we'll try to do something on our front end, but that's just something maybe you could look into.
Yeah, and thank you for your comment, Alex. Maybe just one kind of lead, but not something I'm prepared to talk about today is, you know, actually that's something kind of forward-thinking that is in the works in terms of what this is kind of leading work towards that future work, if that makes sense. So I appreciate that comment.
Sounds great. Looking forward to it.
Thank you.
Michael from YesNet. Very nice presentation. I really like that. I have one quick comment for the Google person. If you don't want to get rate limited from upstream authoritatives, when you ask me in any query, don't expire the entire cache of records that I send you if I happen to send you an NSEC3 param with a 0 TTL. You do that, and that causes problems for me. So.
Yeah, sorry, I'll just repeat, Alex. We had a conversation about that earlier today because of that very behavior.
And the question I had is, did you try to weight at all any of the domains that you looked at based on whether they are known or thought to have DNSSEC signed zones, like .govs and ISC.org and things like that?
Yeah, and that's actually a really great question, because one of the greater questions is not just, hey, we found all these popular domains, but really, if you look at where kind of which of these domains are the most abused because of the size. So in this case, we were thinking performance. Okay, these are popular domains, they must be well provisioned, you've got TLDs, you've got popular websites, etc. And so the idea was, hey, let's start with this. Secondarily, and this is a little bit trickier problem, because if you're going for size, you know, you could say go for .gov domains because we know they had the mandate. Go for, you know, .nl or .cz or whatever. You know, some places where they have a large percentage of DNSSEC deployment. And that's where we actually plan to go next. Selecting them is a little bit trickier, but the point is, can we actually look at measuring not just the impact, but the reduction as well, based on using some of these same principles. So the short answer is no, we didn't do it here, but we plan to. Okay, sorry.
Hi, my name is Andrew Sullivan, and I work for Oracle, but I don't speak for them. I've been informed that that's an important disclaimer. One of the things that seems to me to be an implication of what you presented here is the potential that RRL needs to become adaptive. because the potential here, of course, is that an attacker can use this very technique in order to figure out precisely where your threshold is, and then get enough of a bot in order to, you know, fill your entire capability, even though every single client is underneath your threshold. So have you looked into that? You know, what happens if, right, because it becomes pretty obvious, like just looking at some back of the envelope here things, that you could very quickly figure out the capabilities of a name server given this technique, yeah?
Yeah, and very great thought. I'm going to refer you to a very well-documented DNS reactions post that covers this exact topic.
We better cut the lines there, I'm sorry. So, Brian, you're the last one, because we're doing a DDoS attack on afternoon tea. So, last question, thank you. Sorry,
Ralph, I'll catch you offline.
Just to follow up on the mention of cookies. I think it would be interesting, even if you're not testing both cookies and rate limiting at the same time, to even identify of those pairs which seem to support cookies, DNS cookies. So I think that would help inform other researchers doing other similar related research. You didn't look at that, did you?
I didn't in this particular test, but actually we do have thoughts to do that in the future as well, again, as leading research to other stuff we're doing. And trust me, I love cookies, so.
Yes. And I would suggest if you do look at it, look at cookies and RRL at the same time, see if cookies allow you to avoid RRL.
Yeah, it's a great idea. Thank you, Brian.
And thank you, Casey. And once Keith has said a few words, cookies are right outside there. Have as many DNS cookies as you need.
Yes, just a quick reminder that there are still some social tickets for this evening left. Please collect them at the registration desk before they go during this break. We resume in 30 minutes. Thanks. Thanks, Jeff.